Welcome to SMAP. I am Dave Cederberg. I'm the outreach coordinator for physics and astronomy here at Purdue. We have a great program this morning. We have a professor from Purdue. He has quite a varied history. In fact, I think we kind of maybe stole him away from NASA and the Jet Propulsion Laboratory, but we're glad to have him here. And his name is Roger Wiens, Professor Wiens. And he'll get started here in just a minute. We've got four TAs, teaching assistants with us. We have Roy, Kai, Mariana, and Trevor. And they are here to join us to maybe help answer your questions and help keep things going and maybe think of some questions of their own that they think you might want to know. We are informal, so if you have a question, feel free to unmute yourself, put something in the chat or use an emoji, raise your hand. But we love to hear from you. We love to see you. If you don't mind being seen, we're glad to have your camera on if you want to ask a question and talk to us. So I think let's just dive in and get started. I think without further ado, Roger, Professor Wiens, are you ready to get started?
Yes, for sure. And by the way, when before we start, I'll also mention thanks, Dr. Sederberg, for allowing me to come and talk. And just to bring it back to your t-shirts, I am wearing, thanks to you, one of these SMAP t-shirts. So you can see that logo right here. But I'm also wearing my Mars Science Laboratory shirt that I often wear when I give these talks and when I do the Mars operations. So thanks for the t-shirt and so happy to be here.
Well, let me just say you've been smacked.
Yeah. I grew up in a small town in western Minnesota. I did not know I had no idea what I was going to do when I grew up. Mostly I knew about farmers and a few retail people in the town and pastors and so on. So I really didn't know much about engineering or scientists at all. So it was a very interesting path that I got led down. My brother and I were extremely interested in science, but we were like the only ones in our small town. And so we assembled a telescope in time for a close approach of Mars. So every 27 months, so about every 2 years, Mars comes close to the Earth as they pass in their orbits. And we got this telescope put together in time to look at the different features of Mars. And you can actually see them through our telescope is about this big in terms of the diameter. It's about 15 centimeters, 6 inches. And so we were sketching different features on Mars, and we also had a hobby of building and launching model rockets. And I had no idea that would eventually lead me to taking pictures on Mars and running an instrument team there. So a lot has happened in the meantime, but I've been on 2 Mars missions now, leading these instrument teams, and it's been just fabulous. I built the instruments in New Mexico at Los Alamos National Laboratory, which contracted with NASA to build these. And then half of each of these Mars instruments was built in France because I made friends with somebody who went back to France and proposed that to the French Space Agency. So then with that, we got these instruments built and delivered to Mars. So I'll show you a little bit of that as we go along. So I don't know if you had any questions right off the bat on that. I'll also mention a book that has more information about how this all got going. But maybe I should go into the talk from here. So let me share my screen and let's dive in. But I want to ask, first of all, what do you know about Mars that is different from Earth? And maybe TAs, if you can help, if there's things in the chat, or people can just maybe I don't know if you raise your hand or to speak up, but what is different about Mars from Earth? Big differences.
It's red.
Yep. And you know why it's red? It's red because there's a lot of rust on Mars. There's a lot of iron that is oxidized. The surface of Mars is iron rich. What other difference is there between Earth and Mars? Somebody else.
There's no atmosphere, I believe.
Yeah, you're very close. There's almost no atmosphere. The atmosphere on Mars is about 1% as thick as on Earth, and that makes a big difference for a lot of things that I'll talk about. Anyone else?
We got a or an answer in the chat. There's a huge gravitational difference.
Yeah, so Mars is only 38% as has only 38% of Earth's gravity on the surface. And those things are actually linked together. If there's more answers, I'm going to just skip that for now, just so I can go on. But Mars and Earth are different sizes. So these are scale sort of images of Earth and Mars, and you can see that redness. You can see there's no real oceans or clouds to speak of, and this planet is much smaller. And those two are linked because if you have not very much gravity on a planet, it cannot hold an atmosphere. We don't actually think about that very often, but the atmosphere is held to our Earth by the same gravity that holds us down. And we think that over time, in fact, we have very, very good evidence that over time, Mars lost its atmosphere that it once had. And that's why it has only 1% of the air that Earth has now. But if we were to go back in time, then Mars would likely have had an atmosphere once. And if it had an atmosphere, it would have been warmer because of the greenhouse effect that our atmosphere gives us. And so we think that Mars was really much more habitable in the past. And we have lots of evidence for that. So we'll talk about that as we go along. So just looking at sort of in caricature, we were asking the question, was Mars ever like this, where you see these oceans or big bodies of water, you see land. This picture shows some green on the land, and we don't think Mars ever had green like in green plants. That's because chlorophyll came into the Earth's environment a lot later in Earth's history. And so we don't, if we think Mars did have life at one time, it would have only been single-celled life, like bacteria, and not even the photosynthetic bacteria. It would have been the kind that we call endolithic, which means rock-eating bacteria. We find that in caves on Earth where they don't need any light and the things, kind of organisms like that. So that's what we think we're kind of looking for on Mars. So looking at this picture, we have evidence for the ages of the surface of Mars based on the density of craters on different parts of Mars's surface. So you see this picture with a globe, and the purple parts are the most ancient surfaces. And we think that, looking back at this scale below it, we think that that surface of Mars is almost 4 billion years old, and that the surfaces on the northern hemisphere are mostly almost 3 billion years old. And that's based and compared to the crater density that we have on the moon and other, basically extrapolating. So there are some younger terrains, and those are volcanic from volcanoes that are still somewhat active even today on Mars, not right today, but within the last 50,000 years. And so if we are studying the surface of Mars, we are effectively going back in time. Why is Mars' surface so old? I'll just go ahead and answer that question. But Mars doesn't have water to weather or wear out the surfaces. And also Mars does not, another key ingredient is that Mars does not have plate tectonics. And plate tectonics is where the Earth's crust dives down and sinks under other parts of the crust, and then new parts of the Earth's crust are made at the ocean plate boundaries. And so Mars doesn't have that activity, that sort of active crust like Earth has. And that's probably because it's a smaller planet. And so with both of those things absent, we have this very ancient crust. And that means that it's like looking at a time capsule when we look at the Mars surface. If we look at the same times on Earth, life was confirmed on Earth about three and a half, as old as 3.5 billion years ago. We don't really have much evidence for any life beyond that on Earth. And then the first evidence of any water on Earth is over 4 billion years. So we're looking at the very beginnings of Earth and the beginnings of life on Earth when we look at the surface of Mars. So you could say that Mars helps us to understand Earth's deepest past. So when we explore Mars, we're not just exploring another planet. We're looking at and trying to understand how the Earth came about and how life was created and happened on Earth as well. So I got involved in this about 20 years ago when I was working at the National Laboratory, and I found a colleague who had a little laser, and he could shoot that laser across the room and tell us the composition of a rock. And I thought, this is really cool technology, and let's see if that technology can actually be used by NASA to study Mars or the Moon. And so we put in a proposal for NASA specifically for their big Mars rover. So this is the cover of that proposal. It was 20 years ago now, and so I was the one leading this effort. And the little so that what this shows is the laser beam going and hitting a surface of a rock. It's a place where the rover could never actually have access to. It doesn't have a long enough arm or anything like that. So it shows that we can access areas with this laser that we cannot with other instruments of the rover. And then what we get are the elemental compositions from the light that is emitted by the impact of the laser beam. And I'll show you what that looks like in just a second here. And then we also said we would get very high resolution, very sharp images of that area as well. So that's what we do, and we called this instrument ChemCam because it is a camera, but it also studies chemistry, and it uses a laser. So here is a little video that I have, and I hope this video works on your Zoom, that shows this instrument as we built it, demonstration. So we focus this telescope first, and we're focusing on this little big iron pyrite crystal. And you can see these flashes, I hope. There they are again. And then there it is as a still image. And so you don't see the laser beam. You just see these flashes because the laser beam itself is invisible. It's an infrared beam, but it is a pulsed laser, and it makes this impact that makes these flashes on the rock. So we use those. But I like to joke around because when the public heard that NASA was launching a nuclear-powered rover to Mars, it was going to weigh 1 ton, as much as a car, and this would drive around on the surface. They thought, wow, this rover is going to be doing really big things. And they heard that this was going to have this big laser on it. And so they started asking, do you really blast rocks on Mars? Because they didn't see this video. And so I joke around because we saw this next slide. We saw this picture on the internet about the time of the landing. Somebody was asking if this is what we do on Mars. And I think it's a great joke because we don't do anything like that, of course. So this is actually what the color spectra look like. And so this is plotted. This is all of the light that we are seeing, but it's plotted as wavelength in nanometers, which are very small units, so billionths of a meter. And so the color spectrum that our eyes see is right here. So we can see from the blue all the way in violet all the way over to red over here, just like in a rainbow. So these three spectrometers that give us that light, show us the light that the rock is emitting, they cover an area into the ultraviolet over here, and then some in the violet, which is here, and then different colors in this spectrometer all the way into the near infrared over here. And the positions of these peaks that you see tell us which elements are present, because the wavelength that we have corresponds to an energy of an electron that is decaying back to the ground state of the atoms that we just hit. And so if they're calcium atoms, they will give light at these wavelengths right here where my mouse is right here. I hope you can see my mouse. And so that's what we use. And we calibrate this technique and we get chemistry, and we've gotten more than 1 million spectra over time from Mars. And that's actually available to the public. And I am proposing that in the springtime, we use one of these sessions to look at some of these spectra and determine what composition the rocks are that I'll give you to look at. But before we get there and do that, we have to remember that the rover had to get to Mars. And remember that you said the atmosphere is very thin. It turns out that a parachute doesn't completely work to get down to the surface, but it can slow the rover down. So the scheme is shown on this slide, where first of all we have to use a capsule, just like astronauts have to use on Earth. And so they come in with a capsule, and that capsule then deploys a parachute. But because the atmosphere is so thin, that's still coming down at about 100 miles an hour. So then, but it's slowed from several thousand miles an hour. So the parachute helped a lot. But now we have to have another stage, and that is some powered descent. So we have retro rockets, that is rockets that are slowing it down here. And then there is a stage where this goes and starts to hover above the surface of Mars, and it lowers the rover by a rope. And those ropes then set the rover down, and then the ropes are cut, and this part just flies away. And when I heard about this type of landing scheme, I thought, oh no, this is never going to work, because I had been on a NASA mission before this where we were bringing a capsule like this back to Earth, and the parachutes even failed to deploy, and the thing crashed to the ground. And that was a lot less complicated. And with that not working, I thought, how will this complicated thing ever work on Mars? Because it has to work all on its own. We cannot even control it in real time. And it was going to look like this if everything worked right. Well, it turns out it did work right, and in fact, it's worked right now on 2 different missions. We have 2 rovers like this on Mars, and that's really great. Here are the retro rockets. Let's see, there's my mouse again, and there are the cables lowering that rover. And this is a radar right here, and that radar has to be there to sense how close it is to the ground, so it knows when to let the rover down and put it on the ground. So I have a short video because there were cameras on the rover looking up, and there were cameras on the bottom of the rover looking down at the ground, and there was cameras on this part looking down as well. So we're going to show you all 3 of those in this little video, and there's some sound, and they're all played simultaneously, so you kind of have to watch carefully as this happens, and I hope this works for your video. Here we go. I'm hitting start.
Maneuver.
Yep, so there goes the rover.
Sky crane maneuver has started.
Up here is the sky crane. There's the ground on the right. You can see the rocks, and it's coming closer to the ground. Right there, it's lowering very slowly. About there, it touches the ground.
We're getting signals from MRO.
And then the ropes are cut, and this part just flies away.
Perseverance safely on the surface of Mars, ready to begin seeking the sands.
There we go. And so that was really exciting.
Maneuver.
So that happened twice for me. It happened in 2012, so a long time ago. And that first rover has been exploring Mars for almost 13 years now. And the second rover landed in 2021. And so that's why those people were wearing masks, because that was during COVID. And we've been exploring with the second rover for about 4 years. Now, when we operate a rover on Mars, Mars is something like up to 300 some million miles away. And so we cannot, it's so far away that the radio signals take up to 20 minutes to get there. And so we cannot run a joystick or run it on our computer, because when we send a command, it takes 20 minutes for that command to get there, and then another 20 minutes for it to figure out, for us to figure out what it's done. So we have to operate these rovers completely robotically. So we give them commands and a set of commands for the whole day, and then they operate all day, and then we come back the next day and find out what they did, and then give them another set of commands. Or like on the weekend, like today, the team sent the commands yesterday, and the rover is going to operate all weekend on its own, and we'll come back on Monday and find out what it did. So the rover operations, once it has done something, it actually waits for a satellite to pass overhead. And so that's Mars Reconnaissance Orbiter is one of the main satellites that we use. And the data go to the orbiter and then all the way to Earth from there. We call that a downlink because on Earth it's coming down to us. And NASA has a big set of satellite dishes and they pick up the signal and then they send us the data by internet. And we get that data and we have people who might be in our operations room at Purdue, or now we can work at home as well sometimes, or in our offices. And we look at the data and we check to make sure our instrument is good. And then we say A-OK. We also look at the new surroundings because like on a day like today, the rover is driving a long distance. It's going like about 2 football fields, so not far as a car goes, but still it's going quite a distance away in terms of what you can see from where you're standing in one place sometimes. So then it'll start to look at the new surroundings there. And on Monday, our team will then look at the rocks and pick some targets. So the red dots represent targets that we would be picking for our next analyses. We might have a student who has a list of kinds of targets that he wants to study or some other long-term guidance. And so they will pick those targets. We will then make a plan for the day. And that plan has everything that the rover does. It has driving, it has other instruments in it. And so we all have to share that time and the data that will come back to Earth. There's a quota on how much we can get back, so we share that as well. And the power for the rover, there's a limited amount of power. And so then that plan gets converted into a set of commands. By the way, this plan is showing the time of day on the y-axis here, on the x-axis. So this starts in the morning, here on the left and goes to late in the day here. And the rover only operates usually during the daytime. Then we get these commands built by automatically based on what we put in the plan. And then those commands get sent to the satellite dishes that NASA has. And so then they go back to the rover. We call that uplink. And so they go directly to the rover in that case. And then the rover starts doing its thing for that day. So 2 rovers. And the first rover that landed in 2012 is still operating today. We landed it in a place called Gale Crater. You can look that up online or look for it on a map of Mars. And it's a pretty big crater. It's 90 miles in diameter. And it's the lowest place for about 700 miles around. So if we were looking for a place to show where there was water, this would be a good place. And so we were set to land somewhere in this low part, as you can see by that circle. And then we were planning to drive to Mount Sharp, which is this sedimentary feature. It's 3 miles high in the middle of the crater. So that landing happened safely, as we just showed earlier. And this is what it looked like when we got to the surface. And we started exploring that place. And before this rover had been there, we didn't know if there was ever water long-term or even water like we know it on Earth. But one of the first things that we found in exploring a Gale Crater was this kind of rock. This kind of rock has different color pebbles or clasts. If it's a little bigger than a pebble, we call it a clast. So they're all together here, and they're kind of cemented together all into one sort of bank here. And so what we figured out is that this was part of a river bank on Mars. That's because this kind of rock, what we call a conglomerate, only happens on river banks on the Earth, where the pebbles are brought downstream and then they get cemented together by some of the elements that are in suspension in the water when they start to cement these rocks together. So we found and announced that we had discovered an ancient riverbed on Mars. And not only that, but we found evidence of a lot of lake bed sediments. So the rover started out over here in the low part of the crater, and it turns out that these are all lake bed sediments. And we went up over 1,000 feet in elevation, and that was basically through a lot of layers in the rocks, very fine layers that are about 1 millimeter thick. And going 1,000 feet up with that many layers means that that lake must have been there for a long time if those layers were laid down once per year, as usually happens on Earth. A little layer of sediment at the bottom of a lake. So we figured out through this mission that it had lasted a long time, that lake had lasted a long time. Another thing that happened quite recently, just
Roger, can I
yeah,
interrupt you for just a minute?
yeah,
My
for sure.
I'm trying to let my brain catch up with everything you're talking about. When you mentioned looking for water in the crater, so I'm thinking of water on Earth, and then you mentioned the riverbed. I'm thinking of water on Earth. Of course, we don't have uh, craters on Earth to the extent that they do on Mars. But are you saying that water might have been present within the crater? Uh,
Yes.
okay,
Yep. It probably looked a little bit like this. Yeah, where you had the whole crater full of, or maybe not full of, but at least partially filled with water. Yeah, like this.
so water would have. Well, I guess we haven't talked about how the water might have gotten there, but the crater would have formed first and
Yep.
then filled with water.
Yeah, and we see, as you see in this picture here, we have, there's a channel coming in. We do see channels coming down the crater wall, crater rim, and into that crater. I'll show you another example like that in just a few more slides. But yeah, so there must have been water, there must have been rain and snow for sure on Mars. We know that for a fact, and that's how the water would have come down. Yeah, good question. What we found in Gale Crater is that the lake was filled with water in the past based on the evidence that we have from the rocks, and that the conditions were habitable. We can tell that the water was something that was safe, would have been safe for humans. We can tell that it was sort of a neutral pH. It wasn't acid water, it wasn't alkaline water. So we could have drank that water. And we can tell that from the minerals that were formed in that water. And the building blocks of life were present. We have the element, that is, in terms of elements, we have carbon, we have boron, which is needed, and we have nitrogen and oxygen. And we found some hydrocarbons, that is, some organic materials there that are like we have in oil or coal. We found that there, and the surface is pummeled by radiation. So if we were to be able to dig farther underground, we might find amino acids. We just don't know, which would be more advanced forms of carbon. We also found that Mars had a climate cycle, somewhat like Earth, before it lost most of its water.
Anybody want to ask anything, either chat or just speak up?
How are the rovers powered?
Yeah, good question. Here are both of the rovers. They're almost like twins. And I'm going to point to the back part of the rover, this part right here, if you can see my mouse, in each of those rovers. And back there is their power supply. It is called a radiothermal isotope generator. And basically that's a complicated name for a nuclear battery. It's not a battery like we use in our cars or smoke detectors. We have another battery in the rover that's like that. But this nuclear power supply creates heat, and then the heat is turned into electricity without any moving parts. And there's an inefficient way to do that. We don't usually do that on Earth, but it's very fail-safe and rugged, so we can do that here. And so about 2% of that energy that is given off as heat gets converted into electricity. And the rover has about 100 watts of power continuously. That's not very much, but we have another battery inside the rover that then charges up during the nighttime because a nuclear battery power supply works all the time. And then that other battery charges up during the night, and then we use a lot more power during the daytime to run our instruments and to drive the rover. And so these RTGs use a isotope of plutonium that cannot be used for bombs or weapons, and so it's safe in that sense. And it's radioactive. That's why we call it nuclear. And so it has a half-life of 88 years. And so the power is going down on these rovers. It's going down faster than that because the generation of electricity also degrades somewhat. So the Curiosity rover, the first one, has maybe only about 2/3 of the power that it landed with, or maybe a little over half. And so they degrade over time. We think that Curiosity might last maybe 3 or 5 more years. But so it's done much better than we expected so far, but it will eventually run too low on power. So now I'm going to go on and talk about the Perseverance rover, which is the one that I'm actively working on now. So you can see that they look very much the same. NASA decided to make a second rover like the first. By making it in the same design, they saved a lot of money and using the same landing and all of that. But they used different instruments and a different scientific purpose for the second rover and exploring in a different place. And this rover is called Perseverance. First of all, it looked like this because all of the instruments were competed. And so we had to basically win a pretty competitive competition to get our next instrument on there. And we named this instrument SuperCam because it's like ChemCam, but it has many other details that make it super. So in fact, the science definition team for this rover, which was set up to determine what it should do, said that this instrument has to do mineralogy, not just chemistry. And so we have 2 techniques that we added to do mineralogy. One is to look with infrared vision, and another is to use a technique called Raman spectroscopy. I'm going to show you that here with this video of the instrument that I hope works for you. So we have this mast unit that's up there, and then we have part of the instrument in the body where it's more warm and safe. And then another part is at the back where we shoot these calibration targets just to understand the health and safety of the instrument. And we use these 3 techniques. So 2 of those techniques use the laser. So the first one I showed you already, and that one is called LIBS, where we zap the rocks and make this bright light coming from it. But then we make the laser turn to a green color, and we use that to do a technique called Raman spectroscopy that tells us about the mineral content of the rocks. And then we have a third technique called infrared vision or spectroscopy, and that just uses sunlight and we look at the infrared colors in that from the sunlight. And then this will now show us the camera that we use there as well. So it's a color camera, and it's the highest definition camera on the rover for looking at objects that are far away. And finally, we added a microphone, and that microphone is on this little boom here as well. So we can hear the sounds of Mars as well, including things like when the helicopter flew and so on. So this is much more capable, and we've had a lot of fun with this instrument over the last several years. Here is a actual picture of the instrument, and it is sitting behind glass, and I have my nose pressed to the glass. This was the day before we delivered this instrument to the rover, and so it got shipped to California, where at Jet Propulsion Laboratory it got mounted onto the rover. And so this was in 2019, and you can see the big rover is down below these people, and there's the dark part here are parts of the wheels, and they're up on this elevator here, and they're putting the instrument onto the rover right there. You can see it in their hands, and here's another picture. And so there is SuperCam, the mast part of SuperCam, going up on the top of the rover, and then it gets covered in a box, a white box that sits there, and it looks out from that box. So this next rover, Perseverance, was sent to another crater. This one is called Jezero Crater. Jezero actually means lake in, I think, in the Czech language in Eastern Europe. So because it was, I can't remember exactly why it was named Jezero Crater, but that's what its name is. And we picked Jezero Crater because of this part that you see on the right. There is a river that empties into Jezero, or what at one time emptied water into this crater. And we know that because of this, what we call a delta formation. You know that on the Mississippi River, when the Mississippi River empties into the Gulf of Mexico, is bringing a lot of sediment with it. And that sediment gets laid down just at the end of the river in the Gulf of Mexico, where that is where the water is getting deeper. And that very same thing happened here. We can see it from orbit. This picture was taken from orbit. And you can see the course of the river, in fact, in different places where it's meandering or moving to different directions. And all that time, it was laying down mud or gravel or sand from up the river where it had moved it. And we wanted to see this on another planet. This is really great evidence of river action. And if you were to look for life on another planet, this might be one of the best places to look for it. When we actually drill and get oil from underground, it is usually from an ancient river delta area. That is where we have the most organic material concentrated in terrestrial areas. And so that would be a very ancient delta on Earth that's of course been covered up and so on. So we want to go find that place on Mars. And so that's why we landed near there. And we knew from orbit also that there's some clay minerals there. I'm going to skip past this really and show you the landing. So this landing, we actually snapped the picture from a satellite that here you can see that delta formation in this satellite picture. And in this picture that was taken right during the landing, you can see the parachute and the capsule if you blow up this part of the image. And so this showed exactly what was happening with the spacecraft as it was coming down. And in fact, it landed right about here. So not on the delta, but very close to it. So about a mile away. Here we see a picture from shortly after the landing. This was about 30 days after the landing, and it was one of the first flights of the Ingenuity helicopter. So that's really beautiful. But in the background, we have the part of this delta is part of the rocks that you see back there. And then actually down here, and the crater rim is up above that. And then this part here is part of the delta as well. And so we started to go to the delta, but first of all, we explored the bottom of the crater where we landed. And some of the rocks there looked like this, really close up. This is a close-up picture from SuperCam with some enhanced color, but this was a greenish rock, and it has a very interesting kind of minerals. You can see the shape of the minerals there, and the minerals are called olivine. It happens in Hawaii on the Earth that a lot of olivine minerals are created. So we found that the bottom of that crater was not like a lake bed anymore. It had igneous materials in it. But this delta was certainly sedimentary from the river. And in fact, if we look at the shape of the rock layers, we can see that delta where as the delta is forming and the river is going out into the lake, it is depositing more material on a sloping part like this. And the technical word for that for geologists is foresets. as a delta is forming between the bottom sets and the top sets. And so we knew that this was a river delta for sure when we saw that. So here is the path that we've taken in 4 years with the rover. And this is the scale bar down here on the left is 2 kilometers. The text at the top says we've gone 23 miles. So we spent the first year exploring the floor, the second year exploring the delta, and the third year exploring around the river and starting up the rim. And here we are, the fourth and starting the 5th year soon. And we're on the delta, on the rim of the crater. Each of these little icons is a sample that we collected. And this helicopter icon here is where the Ingenuity helicopter ended. It had 72 flights, and then it actually broke. But it did so much better than we expected it to. We thought it would last only a few flights. So here's a picture from just this week where the rover is. We're down, this is looking back up at the rim of the crater, and we're still exploring. I want to show you one spot where we were actually in the river valley. So this is what it looked like there. And it's a lighter color rock. And this really caught our attention because there's a certain kind of rock that we were looking at here, which had iron sulfide in these white areas. And it's in a sedimentary rock. And on Earth, when we find a bright white spot, it's reduced iron. Iron usually makes things red. And so when I was in Arches National Park, I was looking at a lot of sandstone, and this is in Arches National Park. And we had you see these spots where it's all of a sudden white in a round area. That is almost certainly from rock-eating bacteria, and that's what we see on Earth. And so the question is, what was happening on Mars to make these light-colored spots here that have iron sulfide in them? And we don't really know. That's why we would like to bring a sample back to Earth, and this rover is designed to collect those samples. So this is in fact, what happens as we collect a sample, we take a drill, and that drill is hollow, and that drill then brings the sample back into the rover like this. There's a turret that spins a tube with the sample in it, and then another arm that grabs that tube, and it takes a picture of that sample and puts a cap on that tube, and then puts it in storage. And we have a little storage area over on the left side of the rover, right over there. So that's what we've been doing. Here is a picture of one of the samples that we have. So you can see the rock inside of that drill right there. Looks a little messy because drilling is dirty, of course, in a dusty planet. And we have 33 sample tubes that are prepared. We would love to bring these back to Earth because we can do much more on Earth to study them than we can on Mars, especially trying to understand if there was ever life on Mars. And so we would like to do that, and we think that would happen before we bring people back to Earth. I don't know if any of you have seen the movie The Martian, but you should watch it if you haven't. That's about some people getting stranded on Mars. We actually have an experiment on this rover that made oxygen on Mars, and so that was this little device. And so most of the thin atmosphere on Mars is CO2, but here's oxygen production that we showed we could do that. So if we were to have humans on Mars, we would make a much bigger version of that so that they would have oxygen to breathe. I'll just mention that I wrote this book, and it was about my first exploration, building the ChemCam instrument, and how I got from high school all the way to doing that. So if you want something like this, you can find it online, put it on your Christmas list or whatever. It tells you about that. And I'm going to end with a little outtake from the movie The Martian, where Matt Damon has the ChemCam instrument.
Hey, Johansson. I know you don't like it when I touch the ChemCam, but I'm touching the ChemCam. A lot. So
thanks. I think I took a little longer than I was thinking I would, so I hope it didn't take too long. I hope you enjoyed that.
Professor Wiens, that was fantastic. We had a couple of questions pop up, and I'll just bring one up. Luke asked in chat during the session about would life have developed or would develop on Mars, would have developed on Mars, similarly to what it might have on Earth? Would there be a fair comparison?
Yeah, that's a great question. And we don't know if there was life on Mars, whether it would be related to Earth, because the two planets are kind of close, and life could have jumped from one planet to the other. We actually have meteorites from Mars on Earth, so we know that material has crossed between the two planets. So it's possible that life would be related. Or it could be completely independent if life starts in different places. We don't know how that happens. We're still learning about a lot about that. And then once it develops, well, it develops based on, as we understand it, it's basically develops based on the environment. And on Earth, the environment, of course, became good for advanced life. On Mars, it's not. So we just don't know. That's why we're very curious about this, to explore how everything is out there.
Well, there's a follow-up question. Which kingdom of life was most likely to have been on Mars if there was life at all?
Oh yeah, well, we have something called archaea, and then we have the flora and the fauna that developed from that, more or less, although they kind of branched out. But there is something called the last universal common ancestor called Luca, and so somehow life was advanced to that stage from before that. And so we just don't know much about it. But I mean, rock-eating bacteria is part of that archaea. Yeah, those are good questions, and those are ones that we just don't know the answer to. And so, great questions.
I might actually jump in as well. And
Sure.
so I do some work on the origin of life, and so we think about some stuff like this. And so while Professor Wiens did a really good answer, the archaea especially, we would think the life would not be as developed as he mentioned earlier. And
Yeah.
so we would think of this life wouldn't really have like a cell wall, like life on Earth. But it's very hard to think about life that didn't exactly evolve how we did. So think about how would life look differently with different energy sources, a different atmosphere, all those things. So like Professor Wiens said, this is a question that a lot of people are studying now, and hopefully if we get back some samples, we can help answer some of those questions.
Yeah. And Mariana is one of those. Yeah. Thanks.
We got another question in the chat. Can you explain a little more about how the light spectroscopy works and what happens when the laser beam hits the rocks and how those plots are generated?
Yeah. The laser beam only is active for about 4 or 5 billionths of a second. So, and we have the light from the laser. It's expanded out to the size of that telescope, and then it's focused to a spot the size of a pinhead, as I say. And so the energy density during that time is actually more than 10 megawatts per square millimeter. It's actually smaller than a square millimeter, but yeah, so we have something close to a megawatt, but it's so short that it doesn't take much energy, much power from the rover actually. And when that happens, that superheats that surface, that little tiny spot. And so that surface, then the atoms that are there, they actually go flying off with the temperature of the surface of the sun at 10,000 degrees, basically, or 5,000 degrees. And so when they're coming screaming off, then they cool down eventually, and that's when they give off that light. But just like atoms in the sun give off light. And so then we have the telescope that's part of ChemCam and SuperCam that collect that light. We put it in an optical fiber The light goes into the end of an optical fiber. It goes down from the top of the rover down to the body of the rover, and that's where we have what we call an optical spectrometer, and it has something that we call a diffraction grating. That is a piece of glass or mirror that actually splits the light out into the rainbow of colors. And then we simply have a detector there that just collects the rainbow of colors as from left to right. So we know like red is on one side and blue is purple is on the other. And by the position on that detector, we know the color that it represents. And then we plot that just as I showed you. And that's how it works. And we can maybe hopefully talk more about that if we do an exercise on that in the spring. Great question.
And we do have two other questions here that kind of go hand in hand. The first one is, will there be more Mars rovers, landers, helicopters in the near future? And the second one, how are we planning on getting the samples back to Earth?
Yeah, let me start with the first one and just say we had a mission that was in development to bring the samples back. It's really complicated, and so it was in work, but it got revised, and then basically the priorities changed. Because now with the current administration, there's a lot of focus on sending astronauts into space. And that actually costs a lot more money. We could actually have done 7 Mars sample return missions for the cost of what we've done to send one mission around the moon and back at this point without any astronauts in developing this stuff for the moon. So the priorities of NASA have changed, and so we don't have a plan currently for getting these samples back. But it's a very high priority for the scientists. And so if NASA basically goes back to looking at the science priorities that the scientists have said, then they will put this as a priority again sometime, but we're not sure how soon. And so that plan would be to have a rocket that would actually be landed on Mars and launch off of Mars and bring samples into low Mars orbit. They would then get handed off to another mission that would bring them back to Earth. And so we hope that happens sometime.
I think another question asked about how often is precipitation on Mars?
Yeah, so now it never happens because the atmosphere is too thin to actually support rain or snow. Actually, part of the carbon dioxide, dry ice, precipitates at the poles in winter. So part of its atmosphere actually snows out. But in the past, we don't know how often precipitation would have happened because, of course, that would have been 3 billion years ago. But yeah, so we're trying to learn a lot more about that, but nothing right now. So yeah.
So here on Earth, we have like this rock-eating bacteria in caves, and they make like biofilms and stuff. We were talking about that.
Yeah.
So how do we know there isn't still life like that on Mars, just underground or?
I think I have I'm not sure if I have time to show it, but it's actually the very next slide. Let me see do you mind if I share one slide here still, and I'll just show this quickly. Yeah, so this is if you can see that. Yeah, so there are caves on Mars, and this is an opening of a cave. They are basically lava tube caves. So they're like the kind of caves that are in the Hawaiian volcanoes and so on. And so this one is really big. It's like the ceiling of that cave caved in. And so there's a hole here that's 1.5 football fields in diameter. And it's at least like a tenth of a mile to the bottom, something like that. And so these are absolutely huge. And I have proposed to actually put a small helicopter that would explore into one of these caves. I actually won an award for this concept several years ago, and we're working on an instrument called OrganiCam to try to look for that. So a really good question, and I'm happy to share that. I'm going to give a talk in December at a conference on this kind of concept. So yeah. it's fun thinking about it for the future.
We have another question if we have the time. Where will Perseverance go to study after leaving the crater?
Oh, yeah. So, up until now, we were being told what to do by the Mars Sample Return Program. And then this summer, they said, well, with the change of priorities of NASA overall, we're not sure what you should do next. And so we have several plans in the works now. One would be to go back to this riverbed where we found the really interesting samples and spend more time there. And that would also potentially set us up for where we could leave samples for a return mission. But the other idea is to study the crater rim for several more years and then just go farther south, where there's some more river valleys and other very ancient terrain that's never been explored. And so we have these two choices, and both of them are really good choices. I was hoping we could explore the river valley and then head south, but I just don't know if we can do both. So we'll just see what happens. So I would have to say, stay tuned to the news over the next year or two or three and just see what we do.
Roger, I have a question or two from maybe a more personal perspective. In your professional career, doing the kind of work you've done, working for the various agencies, have there been any times where you were really just kind of felt the end of your rope and discouraged and maybe just thought about giving up?
Oh yeah, actually, in this book, Red Rover, I tell about where NASA canceled our instrument. It was kind of a political thing, maybe a little bit like the Mars Sample Return now, where they had other priorities, and so they wanted to, and they thought they could do some things politically. And so they canceled our instrument, and they actually, to justify that, started telling the press that I was a bad person. Can you believe that? Maybe you can, because you don't know me. But anyway, it was just a really terrible time, and I didn't know what the future would hold. I figured I was out, and that I would probably get a pay cut, and everything else would happen. Maybe I'd get fired. And so I at that time, I'll just say this: I prayed a lot. I believe in that, and there was an amazing turnaround, and I can't go into it here, but it's in the book, and it just a startling way that things turned around, and this all I got put back on the mission, and I've gotten awards and so on since. So it's important to understand that we do need to persevere through hard times because especially when we're dealing with a lot of money to fund these things, our success or our perspectives can change a lot. And yeah, so that was one example. There have been a number of others like that as well. Thanks for asking.
Professional life has its ups and downs. Research.
Yeah, absolutely.
What will happen with the rovers when the batteries die?
Yeah, I see that question. Uh, so we've thought about that, but never really rehearsed for it. I think some of the first things that would happen is that the rover wouldn't have enough energy to do the energy intensive things, maybe like driving uphill or running some of the energy intensive instruments or the arm. And so it could sit there probably for another couple of years. It might not keep, so there's one part that's kept warm electrically, and that's where ChemCam, the mast unit, actually sits. The rest of the rover is kept warm from the radioactive material. So the electrical power to keep that warm might stop, and then maybe our ChemCam would stop working, and then eventually other things would stop. But we could still probably communicate with that rover for a few years, but it just couldn't go anywhere or do anything. Maybe a little bit like we get when we are older as well, where we can't do as much, but we're still hanging around. But anyway, so that will be a very interesting thing to watch. We can't rescue that rover, but maybe, as you saw with Matt Damon, somebody will come along some years from now and find our instruments. So that'd be fun.
Okay, well, we are probably about wrapping up here on time. Anybody else have a last minute question? While you think about maybe a last minute question, I watched, one of the earlier rovers on Mars was Opportunity, and they made a video, a movie, a documentary movie about this rover, and it was called Good Night Oppie. And when you talk
Yep.
about what happens when things start to come to an end, I'm going to throw a link here in the chat, and if you're interested, it's a great movie.
Yep.
It talks about Roger. I'm sure you sometimes feel like these rovers are your child, and
Oh, yeah.
I'm very attached to them, and they're like a pet. And so, if you're interested in a good film, check out Goodnight Oppie. It's quite worth the watch. It's available on Amazon Prime.
Yeah.
Okay, let's take a minute and thank you, Roger, for your time to prepare this talk and your presentation. We look forward to maybe doing something in the spring with some actual data from the rover, and we'll put that on target. So,
Yeah, we'll keep in touch.
okay.
My pleasure.
Okay, great. Thank you all for coming, and thank you to our TAs for being here and watching the chat and helping out, and especially to Professor Wiens. Thank you very much. See you all next time on Saturday Morning Astro. Bye-bye.